Hello, everyone. Welcome to our virtual lecture series. My name is Ruarasha Nyabando, and I am your host for today. Today, we have with us Raja GuhaThakurta. Raja GuhaThakurta is a professor and department chair of astronomy and astrophysics at the University of California, Santa Cruz. His research is on galaxies, their structure and dynamics, dark matter content, cannibalism history, chemical enrichment, etc. He is the founder and faculty director of UCSC's Science Internship Program. He and his colleagues have recently launched the Creating Equity in STEAM umbrella of programs, including the Scientists Program. I will now hand over to Raja. Thank you so much for joining us today.
Virashi, thank you very much for that kind introduction. Can you hear me okay?
Yes, we can.
You can. Okay, excellent. I'm going to share my screen. I assume you can see my screen. I'm going to share my PowerPoint slides. Do you see a field of galaxies right now?
Yes, we can.
Thank you. All right. Um, um, I am going to spend the next 20-25 minutes talking about two topics. I want to present some highlights from our group's astrophysics research. And then, exactly as Rubarashi mentioned, we have several STEAM, science, technology, engineering, art, mathematics. That's what STEAM stands for. Several STEAM research opportunities for African students in school, college, and even university. I've been a professor at the University of California, Santa Cruz for nearly 3 decades. And for the last half of that period, so the last 15 years or so, um, we've been developing these programs, and we are very proud that students from Harare, Zimbabwe, have taken part in these programs last year and this year. We have other students from Africa who are starting to take part in these programs, and I wanted to share some of those with you. I also want to thank Google in Mountain View, California. 7 years ago, I spent close to a year there, and they've helped me develop and expand many of these programs that you'll hear about today. I assume you can see my slides changing. I've just switched to a new slide that is really about our own galaxy, the Milky Way. And what I'm about to show you is a time lapse of our Milky Way that was put together by my friend John Rockman, physics teacher in California. But he actually took these pictures from Masai Mara in Kenya. So close to the equator, he took a series of wide-angle pictures with his digital SLR camera. These were about 30-second long exposures, and there was a series of them that he stitched into this time lapse. I'm going to remove the label so you can focus on the movie. And what you see is this beautiful African sky and the Milky Way appearing to sweep across the sky. You can see shooting stars, you can see lightning, clouds, and you can see all kinds of astronomical and atmospheric phenomena and human-made phenomena as the Milky Way appears to sweep through the sky. I'll play this one more time. You can see the sky getting darker. You'll see some shooting stars, some lightning, certainly clouds going by. The tree is fluttering in the breeze, but someone will turn the light off as it gets dark. The sky, the majestic Milky Way, our home, is sweeping across the sky, is appearing to sweep across the sky. Of course, it's appearing to sweep across our sky because the Earth is rotating. And that is, of course, something that we have to account for whenever we take pictures of anything. We have to track the sky because the Earth is rotating. One of the galaxies my group studies is the Andromeda Galaxy, and I wanted to share this series of mosaic images. These are digital mosaics of Andromeda. When we first took these images, it was 30 years ago, 1992, when we first took these images. They were the first digital mosaics of the Andromeda Galaxy. And you're seeing the same image, but at 4 different contrast level. You see low contrast on the left here, where you can see the center of Andromeda and some details of its disk. You can see much more details of the disk in the second and third picture, where we've cranked up the contrast level. And in the fourth picture, you really can't see the details of the disk or the central region, but you can see the details in the outskirts of the galaxy. And in this image, you see that Andromeda has two companion galaxies very close to it. This galaxy that's to the upper right here in this picture is a companion. And there's another galaxy that's to the left that's just off the edge. The center of that small galaxy is off the edge of our image. And it is in the, as we go to higher contrast, you can see more of that galaxy, or even over here. Dhruva mentioned cannibalism. Andromeda is in the process of eating these smaller galaxies. Eating meaning it is shredding them and stealing their stars. So this is in the process of happening. This is something we study in our research group. And this was really a proud moment for our students, Andreas Berlin, Phil Choi, and I was working with a colleague, Shomak Rai Chaudhary. We put together this digital mosaic of Andromeda. Since then, there have been many beautiful images of Andromeda, including this one by Robert Gendler. Again, you can see now the orientation is different, but you can see the two galaxies near Andromeda that it is in the process of cannibalizing. Now, we use a telescope in Hawaii, on the big island of Hawaii, on the summit of Mauna Kea, to study the Andromeda galaxy. My research group does. In fact, I'm going there in 2 months' time, in September, to study Andromeda. And I will show you a picture of the telescopes. They're appearing in the foreground of the galaxy. There they are. This is a photograph taken by Laurie Hatch, my friend. She's a very talented photographer. This is a Mauna Kea sunset showing the two Keck telescopes. These are the largest ground-based optical telescopes. They're 10 meters in diameter. They have a segmented mirror, very much like the segmented mirror of the James Webb telescope. James Webb has 18 segments. These have, let's see, 6, 12, 18. They have 36 segments, the Keck telescopes, each of the Keck telescopes. There are two copies, two slightly different sets of instruments in them, two telescopes. We use the Keck 2 telescope. I also want to show you some images that we have taken with the Hubble telescope. In the lower left, you see the logo for our survey. It's called PHAT, Panchromatic Hubble Andromeda Treasury, where Hubble refers to the Hubble telescope. This is a cartoon of the Hubble telescope. And we've taken images in 6 different filters, from the ultraviolet to ultraviolet filters, to visible light filters, and 2 infrared filters. So I'll show you the details of that, but it took us 4 years to complete this survey. It took 828 orbits of Hubble around the Earth. Each orbit lasts 90 minutes. For about 1 hour out of those 90 minutes, we can observe Andromeda. And like I said, in 6 filters, from the ultraviolet to the near infrared. This survey was led by my friend and colleague, Professor Julian Del Canton, who was then at the University of Washington. But we at UC Santa Cruz are part of this team, and we use the Keck telescope that you saw on the previous slide to take spectra of stars. Now, you see the Andromeda galaxy again here. You see the full moon to scale. The Andromeda is very big in the sky, but low contrast. So only in images like this can you see the details of Andromeda. Just with our eyes or binoculars, we can't see so many details in Andromeda. Now, these are the 2 companion galaxies that Andromeda is cannibalizing. And this outline, this white outline, is what is the area of Andromeda that was imaged by the Hubble telescope in the course of this survey. So what I want to show you next are the details of a section of this outlined image. Okay, so I'm going to switch slides. And what we're going to do is we're going to zoom in to Andromeda. Andromeda is right there. It is 2.5 million light years away. 2.5 million light years away. This arc is the arc of our Milky Way galaxy. You can see lots of stars, gas and dust. This gas and dust is creating these dark lanes. So I'm going to remove the label and I'm going to zoom in. So again, watch for Andromeda as we zoom in. There's Andromeda. You can see one of its companion galaxies right there next to it. But watch what happens when we zoom in. There's the companion galaxy. There's another companion. So as we zoom into Andromeda, you can see many more details. You can see the details of the gas clouds and dust clouds that are blocking light. You can actually see individual stars in the Andromeda galaxy that are all 2.5 million light years away from us. As we pan across this image, you can see dark patches where dust is blocking the light of stars. But Andromeda is made up of easily a few 100 billion stars. That is a small number with 11 zeros after it. Okay, so a few 100 billion stars. So we use this image and spectra from the Keck telescope to do our research. And one of the things we study is the collision between galaxies. Rubarashi mentioned cannibalism. We use computer simulations and we use actual studies of galaxies, images of galaxies, spectra of galaxies, to understand what happens when galaxies collide. So I'm going to remove the label so you can focus on the movie. Here are two galaxies that are about to collide. These are computer simulations of two galaxies. They are disk galaxies that are spinning. And right before they collide, here are two real galaxies that are about to collide, two real galaxies. We go back to the computer simulation, and the two galaxies get closer together, and they start to intersect each other. And right there, we stop the computer simulation, change our perspective, change the viewing angle. And here are two real galaxies that are in the process of intersecting. We go back to our computer simulation, and you'll notice that each galaxy is stretching out the other one through a process called tidal force, differential gravitational force. Here are two real galaxies that are stretching each other out. We go back to the computer simulation, and the main bodies of the galaxies are about to merge. Right before they merge, we stop the computer simulation right there, change our viewing angle or perspective, and here is a real pair of galaxies that's going through the collision process. Okay, so galaxy collisions are beautiful, they are spectacular, and we understand why colliding galaxies look the way they do. They look really beautiful. They're among the most beautiful objects in the sky. Again, we've stopped our computer simulation, we're changing our perspective. Here's a final pair of galaxies that are in the process of colliding, late in the collision process. Okay. Now, our own galaxy, the Milky Way, is on a collision course with the Andromeda galaxy, and I wanted to say a little bit about that. About 20 years ago, well, was it 20 years ago? No, 10 years ago, 2012, our group worked with a group in Baltimore, and the study was led by the group in Baltimore. We discovered that Andromeda and the Milky Way are on a collision course with each other. Again, in this video you're about to see, there's Andromeda 2.5 million light years away. And this video shows you a projection of what our future will look like. Andromeda will get much bigger in the future because we are approaching it. It is approaching us. So today it looks like this, but in a few billion years, Andromeda will be much bigger. And in 4 or 5 billion years, there will be a spectacular collision between our galaxy and Andromeda. And in the end, there won't be two galaxies, Milky Way and Andromeda, but there will be, in the end, meaning in 7 years, 7 billion light years, 7 billion years from now, the two galaxies will merge into one, as you see in this video. Now, when galaxies merge, you get large galaxies like this. This is a galaxy called Messier 87 that has a giant black hole at its center. So I'm going to zoom in so you can see the details of the central region of this galaxy. And soon, the telescope will lose resolution, so we can't see any details. So now we're going to switch to an artist's conception of what is going on at the center of this galaxy. At the center of this galaxy, there's a supermassive black hole that is causing material to swirl towards it. This is an artist's conception of what is going on in the center. This is not a telescope image. But recently, we've used radio telescopes around the world to take an image of this black hole at the center of this galaxy. And that's what this image looks like. This is an image taken with radio telescopes called the Event Horizon Telescope. It's a set of many telescopes, telescopes in South America, in all over the world, really. Telescopes all over the world have combined their power to see this. And this is a silhouette of a black hole, light bent by the black hole. This is another example of light being bent by gravity. gravity of a cluster. It's like a smiley face. And this was predicted by Albert Einstein, whose picture you see in the left, predicted that light should be bent by gravity. And his friend, Carl Schwarzschild, helped first come up with the concept of a black hole. Now, I feel very connected to both of these people because the son of the person on the right, Carl Schwarzschild, was one of my mentors. Martin Schwarzschild was one of the professors at Princeton University when I was a PhD student there, and he became one of my valued mentors. Now, I want to say a little bit about the people who have affected my trajectory as a scientist. Martin's mentorship of how to do research was really valuable to me. He told stories about how Albert Einstein visited their home after his father, Carl, had passed away. Carl Schwarzschild passed away when he was only in his 30s, I believe, quite young. But Albert Einstein was his close friend and colleague, so visited the Schwarzschild home. They both escaped Nazi Germany between the two world wars. They both reunited in Princeton. Einstein came to the Institute for Advanced Study in Princeton. Martin came to Princeton University, where I later was a PhD student. Einstein had already passed away by the time I came to Princeton. But through Martin's eyes, through Martin's memory, I feel I have one degree of separation to Albert Einstein because of Martin's stories about him. The other person I want to highlight here is Professor Stephen Hawking, the late Stephen Hawking. I was privileged to go to one of his talks. And when I teach my lectures, I teach about Hawking and Bekenstein's theory of radiation from black holes. So I wanted to highlight this person who also has been a huge inspiration. Here are three people who've been role models for me. Vera Rubin was a mentor to me. She was a discoverer of dark matter in galaxies. Another source of inspiration is Subramaniam Chandrasekhar. He is my PhD advisor. So he's my great grand PhD advisor. I had the privilege of meeting him and spending an afternoon with him discussing how research gets done now versus during his time when he was an active researcher. He had already retired by the time I met him. And finally, the person on the right is Mother Teresa. This is my oil painting of Mother Teresa. I was privileged to meet her in 1985, 12 years before she passed away. And again, it was a tremendous source of inspiration for a different reason. Each person, or each of these three people was an inspiration to me in different ways. I want to come back to the universe. And before I talk a little bit more about research opportunities for African students, how am I doing on time, Rubarashi? Am I doing okay? Can I have another 10 minutes to wrap up my talk and or maybe 5-7 minutes to wrap up my talk, leave a few minutes for questions? Is that okay?
Yes, that's okay.
Thank you. So what you see in this slide is a timeline of our universe. I'm going back to the story of our universe. What you see is the Big Bang on the far left and the present universe, the modern universe today, 13.7 billion years after the Big Bang. We think that shortly after the Big Bang, the universe had wrinkles in its fabric, wrinkles caused by the uncertainty associated with quantum mechanics. That was blown up by inflation. The y-axis is the scale of the universe. And so there was a very rapid and dramatic phase of expansion shortly after the Big Bang that took quantum fluctuations and made them from microscopic to macroscopic, made them large, physically large. And it's out of those that galaxies formed. Okay, so this is the story of the universe. So we start with the Big Bang, then quantum fluctuations, then inflation, and then because of gravity, we have galaxies like Andromeda and the Milky Way. We can actually see these quantum fluctuations blown up by inflation when we look at the afterglow from the Big Bang. This is an image of taken with radio telescopes, space-based radio telescopes, sub-millimeter telescopes, that image the afterglow from the Big Bang. You can see hot spots in red and cold spots in dark blue. And we can actually see the quantum fluctuations. This is not an artist's impression. This is an actual map of the afterglow from the Big Bang. If we come a full circle, this is again the afterglow from the Big Bang. Again, you can see hot spots and cold spots. If you take one of these hot spots, each of these hot spots became a galaxy. They first became an infant galaxy, And then through galaxy cannibalism, they became large galaxies like Andromeda. That's what's shown in this picture, even though it's a spiral galaxy like our own. This is a picture of Andromeda. Within it, there are stars. And these stars, some of these stars, all of these stars are producing chemical elements in their interior from the same elements that we study in a chemistry class in the periodic table of elements. But the massive stars among them, they explode at the end of their lives. This is a picture of a stellar explosion as it looks 1,000 years after the explosion. These explosions result in the production and dissemination of heavy elements throughout a galaxy. Out of that, new stars are born. This is our sun and the Earth. They are born with the stardust, with the ashes of previous stars. Out of that, we form complex molecules like proteins and DNA, and we form wonderful living things. This is my son and daughter. My son is the dog. My daughter is the little girl on the right. They are made up of, and you and I are all made up of these wonderful elements created in stellar explosions and during the life and death of stars. Okay, so in the next couple of minutes, I want to spend a little bit of time talking about the Crest umbrella of programs and initiatives that Rubarashi mentioned. This is our logo for Crest. Again, I run Crest with a series of colleagues, Sierra Schneider, Anand Lalria, Amanda Quirk, and Christy Toll. All four of them are or were associated with the University of California, Santa Cruz. CREST stands for Creating Equity in STEAM, Science, Technology, Engineering, Art, and Math. And several students have become involved in this, several students from Africa included. What we're trying to do is we're trying to create equity in STEAM by encouraging young people to think critically in the context of open-ended research under the close mentorship of world experts. CREST stands for that, creating equity, but the way we're doing this is by engaging young people in critical thinking. One of the things we do is we start by saying, just get engaged in a small way. Just take an hour of your time to take part in something called Shadow the Scientist. So we do Shadow the Scientist. Oops, I'm so sorry. I didn't mean to hide my slides. Let me go back to what did I do here? I'm so sorry. How can I get back to my slides here? Hopefully you can see my slides again now. This is Shadow the Scientist, and we do this every week almost. You can take part by joining a Zoom call and seeing how astronomers operate telescopes. You can then learn some of the skills. We teach Python in the context of research. We teach it in the context of astronomy research, but also in biology research. We do this a few times a year. Again, all you need is an internet connection to join. It's free, these programs. We also have a deeper dive, and Rubarashi Moyo, a different Rubarashi, and Nokutenda Saurombe from Zimbabwe have taken part in the science internship program. We also offer something called We Are Stardust. This is in collaboration with Professor Annette Lee. And then we have something called the Sphere Network. We have several other programs that you can take part in if you're interested. So I'm going to stop speaking now and see if we can take questions for the last couple of minutes. I'm going to stop sharing my screen. So hopefully you can see me now. And in the last 6 minutes, I'm hoping people will post questions in the chat, and I'm happy to answer any questions people have about what I've just spoken about.
Thank you so much for the eye-opening talk and for the work that you are doing to increase people's interest in astronomy. One of our questions is, throughout all of your research work, what would you say has been the highlight of all of the research that you've done in astronomy and in astrophysics?
That's a great question, Rubarashi. Thank you for asking that. My answer is probably going to surprise all of you. Astronomy is about grand discoveries in the universe. The universe is a grand place. It's so much bigger than our imagination. Um, our typical imagination allows us to, right? We're used to things on Earth. The universe is so much bigger. I can point to many exciting things about the universe that I've been privileged to be part of. But the most important thing for me to have been an astronomy researcher, to be an astronomy researcher, are the wonderful people I have come into contact with. They are people like you and me who are amazing. They have amazing minds. Their minds are capable of contemplating something as big as the universe, and to just have had the opportunity to speak to some of these people over my 35 years of being an astronomer has been the most important aspect of being an astronomer. I don't know if that answers the question. There's not a single event, but the many people I've come across, some of whom I highlighted in the talk, have been the jewel that I have been privileged to experience during my journey as an astronomer.
Thank you so much. And do you have any words of advice for anyone who wants to go into astronomy, especially coming from Africa, where it's not as popular to pursue such a field?
I do have several words of advice. So I was a physics student in college, and I was I was good at my studies in science and mathematics. I would say if you're interested in astronomy, you have to study a lot of mathematics, physics, statistics, some chemistry. You have to be a very good programmer, a computer programmer. Um, I know that these opportunities are not easy to come by. And I also know that you have to work very hard. I have had to work very hard myself to become a scientist. And but you will have support along the way. Um, if you're interested, please, I would say, please reach out to Knowledge Chikundi. Please reach out to me. We would be very happy to facilitate your journey, to be part of your journey, to be a mentor. Um, that's the advice I want to give you is I want to be part of your journey if you're interested in being an astronomer, and I will do my best to make your journey possible.
Thank you so much. And thank you for coming to speak to us today and leaving us with amazing images that some of us have never seen before. So thank you for spending your time with us and for leaving words of wisdom with us. Thank you.
Rashid, thank you for having me. It's a real privilege to be part of ASBF 2 years now.
Thank you so much.